Hello, this is Sarah Wimdigler, and I'll be walking through my corrections for problem 7 from exam 2. This problem asks us to design a flat belt system where the small pulley has a diameter of 15 inches and spins at 1,140 RPM. The larger pulley spins at half of that speed, and the center distance between the shafts is given as 20 feet. The belt material selected is polyamide A5. From a material property table, I found the following values: a thickness of 0.5 inches, a specific weight of 0.039 pounds per cubic inch, an allowable stress of 275 pounds per inch of width, a pulley correction factor of 0.72, and a friction coefficient of 0.8. To solve this problem, we use the no-slip condition. This requires us to calculate the centrifugal force, Fc, the maximum tight side tension, F1, and the slack side tension, F2. We start by solving for Fc, the centrifugal force. To do that, we first need to find the belt speed, V, and the belt weight per foot, W. The belt speed, V, is found by multiplying pi times the pulley diameter times the RPM, then dividing by 12 to convert inches to feet, and by 60 to convert minutes to seconds. Substituting values, we find that V equals 74.61 feet per second. Next, we calculate the belt weight per foot, W. To do that, we multiply the specific weight by the belt thickness by the belt width, B, then multiplying by 12 to convert inches to feet. Simplifying, we find that W is equal to 0.117 B pounds per foot. We leave B in the expression because the width of the belt is unknown, and solving for B is the goal of this problem. Now that we know V and W, we substitute them into the centrifugal force formula. This gives us Fc equal to 20.22 B. Next, we calculate the maximum tight side tension, F1. The general formula is allowable stress times the pulley correction factor, Cp, times the belt width, B, and times the material correction factor, Cv. For belts made of leather, Cv would be less than 1. But since polyamide is not a leather material, Cv is just 1 in this case, so it does not change the calculation. Thus, we calculate F1 by multiplying the allowable stress by Cp and by the belt width B. Simplifying, we find that F1 is equal to 198 B. Before we can solve for the slack side tension, F2, we first need to calculate the torque, T, delivered by the motor. Torque is based on the adjusted horsepower, which we find by multiplying the nominal horsepower of 100 by the service factor of 1.25. Substituting into the torque formula and solving, we find T equals approximately 6,910.64 inch-pounds. Now that we have the torque, we can solve for the slack side tension, F2. F2 is found by taking the tight side tension, F1, and subtracting 2 times the torque divided by the pulley diameter. Simplifying, we find that F2 is equal to 198B minus 921.42. Before applying the no-slip equation, we also need to find the angle of wrap phi. Here, capital D is the diameter of the larger pulley, and lowercase d is the diameter of the smaller pulley, and C is the center-to-center distance between the shafts. It's also important to note that this formula gives phi in radians, not degrees, so we need to make sure we are working in radians for this calculation. We find capital D by knowing that the large pulley spins at half the speed of the small pulley. This means the large pulley must have double the diameter, or 30 inches. Substituting into the formula and simplifying, we find that phi equals approximately 3.017 radians. Now we can apply the no-slip condition. The equation is F1 minus Fc over F2 minus Fc, which is less than or equal to e raised to Fv. Substituting the expressions for F1, F2, and Fc into the no-slip equation and simplifying, we find this expression. Cross-multiplying and rearranging terms, we solve for B and find it equals approximately 5.67 inches. Thus, the minimum belt width needed to prevent slipping is approximately 5.67 inches. I just want to briefly explain what happened during the exam. I spent a lot of time stuck on problem 6b, which had some missing information, and I ran out of time when I got to problem 7. I had time to write down some relevant equations, but I wasn't able to really use them to solve the problem. That's on me for not budgeting my time better. I'm glad I have the opportunity now to work through the solution and show I understand how to approach it. Thanks for watching my rework. I appreciate the opportunity to revisit this problem and demonstrate a clear understanding of the full solution process.